All right, let's discuss this problem called longest increasing subsequence. Let's have a read. Given an integer array nums, return the length of the longest strictly increasing subsequence. Okay, let's take a look at the example. This is an example. Subsequence would be you take elements in the same, like sort of like you can't change their order, but their relative positions have to remain the same, right? So, for example, in this case, the longest increasing subsequence is 2, 3, 7, 11. So, 2, 3, 7, and sorry, 101. And it could also be 2, I guess, 2, 5, 7, 101. It could also be 2, uh, 3, 7, 18. Essentially, all of them are of length 4, and this is what we get. For this, I guess 0, 1, like these two, 0, 1, and then these 2 and 3. They give the maximum result, and all sevens is just 1. Strict because you want strictly increasing. So you can only take 1, 7. So how do we build that sequence? Um, let's take a look at the example on the whiteboard. So I'll take the first example that's given in the question, and that is all right. Let me retry. Okay, so we have 10, 9, 2, 5, 3, 7, and then we have 101 and 18. Now, the approach that I think of is we essentially want to find the longest increasing subsequence overall. Let's try and find the longest increasing subsequence ending at specific index. So let's focus on longest increasing subsequence ending at each index, right? And see what that would mean. So for 10, the longest increasing subsequence ending at 10 would be this only, right? For 9, the longest increasing subsequence ending at 9 would be what? Well, any guy previous to it is there is no smaller guy smaller than 9, so it has to be just 9. Okay. For 2, again, there is nobody who is smaller than 2, so it has to be just 2 only. Okay. Now for 5. So for 5, it would end at 5, but is there anybody who's smaller than 5? There's only one guy who is smaller than 5, which is 2. And for this guy, the uh, longest subsequence was 2. So now for this guy, we can take 2 comma 5 as the longest sequence, right? Now come to 3. So for 3, is there anything smaller than 3? There is one guy smaller than 3, which is 2, which has a subsequence as 2. So it can be 2 comma 3, right, for this guy. What can be the longest increasing subsequence ending at 7? So who are smaller than 7? Well, 3 is smaller than 7, 5 is smaller than 7, and 2 is smaller than 7. All three of them are smaller than 7. So if you consider the subsequence from 2, so the different options are either you can have 2 comma 7. What did you have at 3? 3 you had 2 comma 3. So you can, sorry, first look at 5. So 5 had 2 comma 5. So we could have 2 comma 5 comma 7, and then we could have 2 comma 3 comma 7, right? All of these three are different possibilities, and obviously the biggest one we'll take. So we'll ignore this. Maybe one of them we can take. So maybe we'll take this one, right? Anyone is fine. For 101, what would you do? So for 101, similarly, it would be uh, 2 and then 3 and then 7 and then 101, right? And for 18, it would be what? Which is small? Who is smaller than 18? 7 is. 7 you got 2, 3, 7, and then 5 also is, but obviously 7 is the largest length. So it would be just 2, 3, 7, and 18. So based on this, we can see, right? For any guy, the longest increasing subsequence ending at that guy is either just that element or that element plus whichever elements are smaller than itself, and whichever from them has the longest length. Now, would it always be the last guy is smaller than this? For example, in this example, but whenever we saw, it was always the last guy smaller than this. Like for example, for 101, the last guy smaller than this was 7. and we just added this, right? For 18, the last smaller was 7, so we got it from this. But would it always hold true? Or do we have to look at all guys which are smaller than this? So maybe let's see if there can be another example which can clarify that bit. So I'm trying to see if there can be, and maybe there can be, right? So for example, an input can be something like 2, 3, 4, 5, and then we can have, hold on. So it could be this, and before this, it can also, hmm, mm, 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 first guy is smaller than this. Hmm. So we are looking at some guy, and for example, let's say 17, and we're looking at this guy. So for example, 2, 3, 4, 5, 17 would be an option, but it could also be something like, what about this? 6, 7, 8, 9, 10, 11, and then yeah, maybe what about um, what about this, right? So in this case, oops. So in this case, if you focus on 17, we can see the last guy smaller than 17 is 5, but that won't give you the best result because from that you will just get 2, 3, 4, 5, 17. But actually, if you look at 11, that would have given you better result because it would have been 6, 7, 8, 9, 10, 11, and then 17. So it's not always the last guy. You have to look at everybody who is smaller than this. For example, in case of 17, everybody is smaller than 17. So either we somehow figure out it's either this 11 and this 5, like we could fix those ranges, or in general, we just get the look at every guy who is smaller than this, and for them, whatever is the LIS ending there, get the max of that, right? So essentially, what I'm saying is uh, I want LIS at I equals to 1 plus max of LIS of j, right? Where all j is less than I, like less in this line, and the value of that guy. So a of j is also less than a of I, right? If there is no such this, then obviously it will be just one. Otherwise, this will also get added. So this is my logic. Let's sort of build it and see if it works in code. So what I'm saying is that I'll have a LIS array. I'll give it the length of nums.length, and what this LIS is uh, length of longest increasing subsequence ending at this index, right? That's what this guy represents. And so obviously for the first guy, you can imagine it will be 1, including that just guy. So LIS of 0 we can set as 1, and we can do um, now we go through each and every number. So for int I equals to 1, I less than nums.length, I plus plus. Now for this, we want to get LIS. So first you get the like the all the guys before this who are smaller than this. So let's define something called as max candidate initialized to 0, and now we'll go through each of those candidates. So int I equals to 0, I is less than j. So all elements to the left of it, I'm checking all of their LISs. So uh, if the element has to be lesser than this guy. So if nums of okay, there is a mistake. It has to be j and j less than I, right? All elements to the left of I. And if that guy is also less than this, then only it will contribute to an increasing subsequence which ends at I, right? So then for that, what then we can do is, and we need another condition. That is the case, and whatever LIS that guy provides, if it's greater than the max candidate, then we'll update the max candidate to the LIS of j. and we will do um, lis of I equals to 1 plus max candidate, right? And we can also maintain the overall max. So maybe initialize max to 1, right? Because at least there will be one element. So max equals to max of max comma ls of I, and eventually we will return max. If we talk about the time complexity of it, okay, so there is this one for loop, and then there is this other for loop which goes through all the elements on the left of this guy. So it's n squared. In terms of space complexity, we are using an extra auxiliary space of size n. So O of n is the space complexity. Let's run and see if there are issues. And we do have some issues. Let's see, j equals to 0, j less than I. Okay, it has to be j plus plus. Let's run. And all three are accepted. And this is our solution. Um, looks correct. We go through each element. For all those elements, you look at all the elements on its left and see whichever one is smaller than this. That can be a part of my LIS, and so I'll check what was the LIS ending there, and whichever of them gives me the maximum one, I take that and add one to that, like add myself to that. And if I didn't find anything, then max in it will remain 0, so I'll just be 1. Yeah, and submit and see if it works. And it does seem to work. All right, now if you look at the problem, it also says, can you come up with an algorithm that runs in O of n log n time complexity? Our current algorithm is clearly O of n squared. Now, can we do something which would be O of n log n? Now, I myself at least couldn't come up with any solution, but we can discuss the solution that leads to O of n log n approach. And the way to do that would be, the understanding how it works is easy. So I'll take an example, again, the same example perhaps that was given in the first input. So here it's 10, 9, 2, 5, 3, 7, and 101 and 18. So the approach for that is basically you go through all of these elements one by one and create multiple sort of groups or DACs. And the way to create a groups or DAC is, you will never add an element to a DAC. You never add a greater element on top of a, like if I have X, I should not add any element more than X on top of it. Instead, I should create a new DAC. And if so, for example, here, um, and so first I'll take 10. I'll add it to this group. Next guy is 9. 9 is smaller. So smaller is fine. Smaller you can just add on top of it. Like so I add 9 here. 2. 2 is again smaller, so that's fine. I will add on top of it. Like I'll add here. I'll add it to the same group. 5. Now I always check with the last guy that I had added into the group, right? So 5 is greater than this last guy. So now I'll create a new group. So this is my new group now, which is 5. Now 3. So now I'll compare this 3 with all those that are possible and see where I can add it, or if I cannot add it at any of the one, then I will add it to the a new group. So 3 is not less than 2, so I cannot add it to this group. 3 is less than 5, so I can add 3 here. 7. 7 is not less than 2, not less than 3, so I'll add it to a different group. 101 is not less than either of 2, 3, and 7, so I'll add 101 to another different group. And 18 is not less than 2, not less than 3, not less than 7, but less than 101, so I can add 18. And so look at the last guys added to all of the group, right? So basically the number of groups that get created is your longest increasing subsequence. And if you want to get the longest increasing subsequence, just take the top element, take the last elements added to each other group. So here 2, 3, 7, 18 is one of the longest increasing subsequences that we can get. It always works. Now, one of the things to note is that at the way that we are doing it, which is we never add a greater element to the group, right? Like in this group, We never added a greater element. In this group, we never added a greater element. Only a smaller element was added, or an equal element would have been added. And if there was a greater one, we added it to a different group. If there was a greater one, we added to a different group. If there was a greater one, we added to a separate group. That ensures that this tops of all the groups is always an increasing sequence, right? Or is always sorted, right? So like when I was trying to see, hey, where I have to uh, add, let's say 3. So when I was adding 3 in that state, I had this 9 and 5, right? Or rather 2 and 5, right? When I was adding this 3, my state was 10, 9, 2, and 5. And in this state, I was adding 3. So 2 and 5 was my sorted array. And where to add a 3, I could do a binary search there, right? Instead of doing a linear search, because this part is always sorted. So essentially, that's the idea. Let's take another example. Uh, so this is the example 0, 1, 0, 3, 2, 3. So what's happening? Okay, so the first group I add 0, and then 1 is greater, so I add a new group. 0 is smaller than the first group, so I can remove this 0, replace, like it's sort of I'm shaping it into towards the algorithm. I could add it to the same group. And I'm only interested really in the top or the last element added to each group. So that's why I'm sort of saying I'll replace this 0 with this 0. 3 is greater than both of them. Now, where to insert this 3? 0 and 1 is a sorted array. Where to insert this 3 would be a binary search, and will tell, hey, you have to add it at the end. So I'll add it at the end 3. 2 again, 0, 1, 3 is a sorted array. Where can I insert 2? And and the way that we are doing is it we don't want to insert into a group from which it is greater, right? We can insert into a group only which from which it is smaller. So 2's index will come here, and at the point of 3, 3 is greater, we can add 2 here, right? So essentially this index where to insert to can be got through uh, a binary search. And last is 3. 3 is, so I removed this, right? I replaced this 3 with 2. And this 3 is greater than all 0, 1, and 2. So I add this 3 here. So my longest increasing subsequence will be the number of groups that I have. And the longest increasing sequence is this 0, 1, 2, and 3. So what am I doing? I'm going through each element in my array. And for every element, I'm doing a binary search, right? So each element I'm going and for each element, I'm doing a binary search in my groups array to find where exactly I can insert it. Whether I have to insert it at a last new index, or I could update one of the its existing groups and add it to that, right? And so that binary search is log n, and so the algorithm comes out to be n log n. Let's try and approach write code for this approach as well. All right, so come to the code. We reset this code. So what we are doing is we are creating a new groups array just for simplicity, and we'll initialize maybe initially if it's completely increasing. If nums is completely increasing, then it's possible that we'll have that many number of groups. So let's initialize it to that much size. So we go groups equals to new nums of length, and let's also do number of groups. How many groups do we have at the begin to begin with? Let's have just one group, right? And we can have the first guy added to the first group, which will be nums of 1, sorry, nums of 0. And then what we'll do is we'll go through each number. So int I equals to 1, I less than nums dot length, I plus plus. And now we'll find the index where whether it will. So let's do a binary search now. So let's say index equals to call some helper binary search function. We are searching in this groups array from 0 to what is the right? Right is num groups minus 1, right? So LR, and what we are searching for is this key nums of I, and index is the position where uh, nums of I should be added. It can be from 0 to num groups minus 1, right? Which means it is added to an existing group, or it can be uh, num groups, which means we are adding a new group, right? So if index equals to num groups, that means we're adding a new group. That means, well, your num groups has to increase, right? And you actually add it. So meaning of that would be groups of whatever this index is. I will add this nums of I, and this number of groups will increase, and I'll do eventually we'll return the number of groups, right? That was the algorithm that we discussed. Let's also do this binary search. So we are doing int binary search. We are given an array, an integer array, and we are given left and right, and we are given a key to search, right? So basic steps, while lsn equals to r, we get the mid. Now obviously if you find the guy, so then you can add it to the same group, right? So if nums of mid is equals to key, well, return this mid. What else can be there? If the middle guy is smaller, if nums of mid is smaller than key, that means if key is bigger than your mid, then obviously you, including mid and all elements to the left, they are smaller than the key, so the key will have to be added. Like you cannot add a greater guy on top of, you can only add a smaller guy, so you have to move search in the right. So then we do r equals to mid plus 1. And what else? Now let's say, so now that means the only condition is nums of mid is greater than key. Now there can be two cases in which that is a good scenario. Ideally, what I would want in this is, typically we'll do, okay, so L equals to mid minus 1, right? Now, however, let's think of some cases. So let's think of one case where you're finally left with a single element. And that single element is, let's say, 4, and you were searching for 10. So if I was searching for 4, if I'm sorry, yeah, if I'm searching for 10, so 10 definitely cannot come on top of 4. It has to come on a new position, right? So new position, that means it is this condition, r equals to mid plus 1. Then we'll break out of this, and once you break out of this, that means here, um, sorry, this is not, that's some mistake I did. Like L would be mid plus 1 and R would be mid minus 1. So this L would have been like one step ahead. So, and for this condition, when I break out, I would want to return this L, which is greater than this, right? For this condition. So in this condition, mid would be 4. 4 is less than 10. So L becomes 1 greater than this. And now this condition will be broken. And so I'll return this greater than this L. That means I have to add a new group, which is fine. But what if this was 11? That means then it comes into this else part, where then I reduce my R to even one lesser than this. Now, so that is where, that means 11 and 10 is lesser than this. I basically want to find the first guy, which is greater than uh, the first guy, which is greater than my search key, right? So I can modify it a little bit, where I can do else if one case is I don't have anything else. That means mid minus 1 is actually less than L, right? That means I don't have anything else. So this is the guy. Or there can be another case where I do have a mid minus one, but that mid minus one, that guy is actually, let's say, so I had this 11, and let's say the other guy was 5, right? And I'm searching for 10, and I'm at this 11, and I say, okay, yeah, 11 can be a possibility, but I also want to look at all other possibilities in the left, and just the next left guy is actually smaller, so it doesn't work, right? So if nums of mid minus 1 is actually less than key, that means for both of these scenarios, also mid is good to be returned, and everything else works like that. So this is the logic. Let's run and see if it works. And we get an error. Let's fix that. Line number 28, nums of mid equals to key. Okay, we have used nums everywhere, so what we define it array here. So let's change it to nums and run. Okay, we get more errors. Return spelling mistake. Let's fix that. And it seems to work. This update. So what this binary search is doing is find the first position which is greater than or equal to key, right? That's essentially what we are searching for, right? First question which is either equal, or if it's greater than, that's there is no left, or the left guy is smaller. That means it is the first greater. Uh, and obviously this special case we already discussed why we're returning L. That was for that case where it was like 4. That was the case where you basically didn't find anything. Like this is essentially the case when you did not find any key within, and so that means you're returning one greater, which in this case would be when we try to search further more towards the right, meaning increasing L to mid plus 1, which is why I will return this L. Now this is good. Um, Now, if you think about it a little bit, yes, we did create this groups array, which gives us a good understanding of it, but we could potentially use the same nums array because always your index will be less than or equal to I, right? So potentially we don't really need a new groups array. We could even just do so. We could even just do use the same nums array and override it, and this num groups will help us to keep the index of how many groups we have actually filled. So that's a slight optimization that we can do, uh, where we just use the nums array everywhere. Yeah, and let's run and see if that works as well. And it works. Let's submit and confirm. And that works as well. All right.